Okay, good morning, everyone. Welcome to AI Accelerator Summit. This is my second time actually being in this summit, and the first time I benefited a lot connecting with people, and I even use them in some of my projects in Comcast. My name is Hamid Nazari. I'm a principal AI scientist in Comcast Labs. We are based at Sunnyvale, very local. And I am going to have a presentation, which is a light presentation of the morning. I don't want to get you guys confused. And that can be considered as a keynote as well. And in the meantime, I am going to chair the conference. And here is the logistic. After I'm done with my presentation, I take questions. We go like with 5 minutes question and answers. And that is going to be a routine for all the speakers. And I am going to introduce the next speakers before they start their presentation as well. For any announcements in between, for example, if you want to just take some bio breaks or taking time for lunch, we are going to have an announcement as well. So any questions so far? Confusion? Nothing. Okay, so let's just roll. What I'm going to present today is a pipeline for computer vision. In fact, that's something that I experienced in the course of a year of development. And there is no math, there is no stat. It is just sharing my experience with you guys. It's basically a computer vision pipeline, both on premise and on the edge. So let me just start with what computer vision is. Computer vision is to extract and understand the content of image, and that image can be a frame of videos. Which if you combine the knowledge set that you get from one frame, you would just get a good understanding of the content of the video. So then the base and foundation of computer vision is just one frame of photo. So we extract basically the description from the image. For example, if you have an image, a dog is walking on the beach, so you can make a model to basically to extract the description, and out of that image, again, if you apply that to each frame of a video, so obviously you can just write up the whole content of a video as well. So if you have, again, a few frames, you can group them in just one and come up with the topic of that specific scene in the video as well. That is what they call grouping and searching image content. And basically there are a lot of GAN, which is generative adversarial models, which helps nowadays with making, if you have a 2D image, two-dimensional, you can just make it 3D dimensional out of that image, which is, I think the technology is moving towards to that path for sales and production, specifically big companies who sells online product, in their product online. They are trying to present any products that they have as a 2D images in a 3D in an AI fashion. Not that they can't just do it manually with 360 degrees cameras, but they want to use that to streamline their processes if they have probably a platform for their sellers, for their third-party sellers, So they load their images, and then they take that image and then make a 3D view of that image automatically. Okay. So this is a very vanilla version of computer vision pipeline. You basically have a camera. That's basically what I worked on. Instead of the camera and having a video stream, you can have just one frame. Again, I'm not going to just repeat that every time. So you have a bunch of cameras or one camera, and then you take that stream of the camera from each camera. The stream comes, and then we run some image processing, which I'm going to explain what image processing is in my next slide. And after cleaning up your images, then you just push it to your computer vision models that you have for inferencing. And if you want it, you can save the frames for the later use, or you basically can save your data in a database for a reporting purpose. So image processing. Image processing is not computer vision. The process basically that you take an image and manipulate that image to prepare that for computer to be fit to computer vision models is called image processing. That can be a process of creating a new image size-wise from existing image that you have. For example, you have a 4K image, but your model doesn't take 4K image. So you change that to 224 pixel to 224 pixels. So that is called image processing. And simplifying the content in some way. Sometimes, I'm sure if you are in computer vision business, you run into a lot of images that has a dark background, and you don't need those dark background. You want to just remove the background. So that considers as a image processing process as well. So sometimes you add different type of filtering, like Fourier filtering using OpenCV. That is image processing as well. Removing noise using different filters. Again, that's considered as image processing. So all of the cropping and resizing, removing noise, all of this stuff are considered as image processing. Up to the point that you take that image and convert that to a 2D or 3D array and prepare it for your model to be input to the model. And here's the challenges of computer vision. Basically, visual world is complex. For example, if I want to count the crowd here in this area, a number of you guys are covered, yourself or occluded some others, which hinders the process of counting the crowd. I may undercount and I may overcount. So this is the complexity, that our vision as a human is complex enough to identify each person differently and separately, but computer vision is not still in that stage. So again, based on the same example, the orientation, sometimes you are interested in learning if someone is just paying attention to specific content. In this case, as an example, is if I want to just make sure person A is looking at me and paying attention to me. And what is a possible way to do that? So I can take that image in a different orientation and then can interpret that image in a different way. That is complex as well. It sounds simple, but when it comes to action, it is complex. Lighting condition, that killed me in my project. So if you have a poor lighting conditions, the cameras get blind very fast. So it's even a little kind of changes in light will drastically impact your model's output. The modern applications of computer vision is, as you are aware of, is object classifications, as I explained in my first slide. For example, if you have a few objects in this table, cup, mugs, bagel, so you want to classify those objects, that's one of the applications. And you can apply the same example to the frame and the videos as well to extract information from videos. Specifically in Comcast, we are very interested in video content analysis because we want to offer products to our customers. So we do we run analytics or computer vision techniques on video frames to understand what they are interested in and what we should offer as an upsell to our customers. Object identifications, example, face. We want to identify a person. And object verifications. Sometimes in some of our facilities, we are interested in just identifying, for example, guns in the crowd. So that is going to be considered as an object verification. And then detection, landmark detection on the face. So if you want to just differentiate two people, we go with the landmark, which is a good paper from 2015, I think. I implemented that one, and it's working properly fine. And object segmentations. These are the things that I could think of. So the promise of deep learning, however, is unlike traditional machine learning that you have a bunch of sparse data and you don't know how to manage it, nowadays deep learning offers a black box solution that you can push your data and then extract the features that is most important to that specific frame. For example, if we have an image of myself with a dark background here, then the dark background will be removed automatically and my face gets detected as a feature or gets extracted and then will be passed or pushed to the next layers of the network. Deep learning is an end-to-end model. You build one, and then you push your image or any type of machine learning model if you want to make, or natural language processing kind of model. So you push your data, and then you get an output. That's an end-to-end black box. Nobody knows what's going on inside of it. If you have many layers, you have to visualize each layer, each neuron, to see what happened in that specific time frame on that neuron, and then how filters impact your images. But we're not interested in how deep learning actually helps us with modeling our images. And you build a model once and reuse it many times, and that is something else that it offers. As it involves with a mathematical and derivative proven process, then it offers a superior performance and accuracy. And it's a general method, easy to learn. You can just have a course for 3 months, 4 months, and then you can just be a deep learning junior engineer, of course. But if you want to build a model or architecture, the way big companies like, I think we have friends here from Apple, Facebook, and Google, the way they are making, of course, it takes a life long to get to that level. Okay, the camera that I use in my project, I use Logitech 1080p and Logitech 4K for proof of concept because, as I said, we are in the Comcast labs and we make a proof of concept and then we turn it to production if that interests any organization across the company. The proof of concept we built with the Logitech 1080p and Logitech 4K. And then in the production in our facilities, I use 4K cameras, use specifically Access 4K, and then replaced it with 8K to get more feature. And I'm hearing that Access is coming up with 10K cameras as well, which is going to be very interesting. There's one other company which I found it interesting. Their product is very powerful and strong in generating 4K frames. It's a Backstreet Ultra 4K. And here is a video, a short video. I want you to just watch to see the quality of the frame that you get out of 4K cameras. See, changing light doesn't impact So you get all features from faces. That means you can process these faces pretty well using the models. In terms of action detection, that was funny though. So in terms of action detection, again, 4K cameras give you enough features that you can process it very accurately. Okay? Moving on. This is an introduction to the models that I experienced. I use OpenCV for Can you just push this? Yeah, thank you so much. I use OpenCV for image processing, and then I use the deep neural network, CNN, YOLO, Faster CNN, LSTM, Faster LSTM, and many more. And then I picked the best out of them. And so here is the reason that we need GPUs for processing our images. I was using 4K images, and the dimension of the image is, as you can see here, you get this many pixels in each frame. So obviously, there are two reasons you can't just process this data. One, you can't just make a model to process this many pixels. Second, you have to downsize the pixels. Third, even if you downsize the pixels, you get as 3 times as what you see here because your images are colorful and 3D arrays. So times it by 3, you get the number of pixels that you're dealing with. So GPU processes data and NumPy arrays as a tensor, and it runs fast processes in the graphic chips, which later I'm going to explain what chips I used and what GPU I used, make it more clear. So more complicated algorithms, of course, as you use, for example, if you want to use simple algorithm with 4 layers of neurons, layers of hidden layers in the deep neural net, so you are dealing with few features. But if you want to go to YOLO based architect, you're dealing with millions of features. So these features requires more processing power. And as I said, tensor processes multi-dimensional arrays. And that these features in a complicated architecture results in a heavier weight matrix to be processed. So that's why we need a GPU. And this is the architecture that I implemented first in my experience. And I had a server here for processing the computer vision models, and the image processing, that was one server, and then with GPU, and then one server to save data in a database, and then there was another server, believe it or not, which is called Synology for Axis cameras. They had their own server. So we are dealing with 1, 2, 3 servers here, 3 maintenance, and installation of operating systems, and setting up everything from scratch. So that was a lot of work, which had nothing to do with computer vision. So how that process worked? Again, so grabbing frames from here, the cameras, and push these frames to image processing. And if you have 2 cameras, which in my case was 15 cameras, you have to have a process to synchronize these frames, because you have to, if you have 15 cameras and you process your frames in a different time frames, you are not going to extract data at the same time from the same scene. So that was a big challenge, synchronization. And then you have computer vision models here to pass each frame to that model, and then save the data in a database and then aggregate it based on the time. So that's basically the steps that I just explained. So for that process, I used NVIDIA GPU, and which you can find it in Amazon Web Services. Nowadays, they offer NVIDIA products as a service. In the Google Cloud, I heard that NVIDIA product is used, and some of the desktop that you buy from Dell, it comes with GPU if you want it, which I used that server, specific server that uses, it was Dell product, I think, and using 4 NVIDIA GPUs. And of course, there's Intel products coming. They have a proprietary kind of use of it in their own servers. So that was a little headache for me to go with Intel. And the requirements for the first pipeline, which was in-premise, was, of course, we need a server, 3 servers to maintain, GPUs, the maintenance of GPUs, and what I mean by maintenance of GPUs, installation of CUDA and all those softwares that NVIDIA offers. If you want to do it yourself, it's a daunting job. But nowadays they come up with the Docker. You can just use the Docker and easily just fire up your machine. Operating system setup, installation of course, computer vision models are very compatible with Ubuntu, but our company required CentOS server to be installed in their server racks. Man, that was crazy. So installation of that server, setting up, making that compatible with OpenCV versioning and NVIDIA and CUDA versioning, that was quite a job. And moving frame from cameras to server to process and synchronization, that was a big deal. Speed, because the cameras were installed away from the server, that was a huge deal as well. I had to manage that speed. And then the security concern, so you grab all those frames in the crowd, in the facilities. You don't want those frames to be shared anywhere with anybody. We had to just transfer those data and image frames securely. So the network bandwidth to process the frames, which were coming from distant camera locations, and a lot of more problems. But we made it through. It was working. It was working fine, but maintenance time and whatever challenges that I just counted, those were killing. So last year, I attended GTC conference, which is held by NVIDIA. It's, by the way, on the corner, I believe, in a few days. GTC is going to have a conference here in San Jose as well. I ran into a chip offered by NVIDIA, which is called Jetson Nano TX2. That is a very powerful chip, extremely powerful. It's not like other chips that you've seen in like Raspberry Pi. It has a GPU built in. Amazing. So I took some of them. I think it was $99. I bought 5 of them and then tried to experiment to change the architecture and pipeline to this way. Grab each frames and then push it to Jetson Nano, process it on premise, and Jetson Nano is like connected to the camera now. And process it right close to the camera and then send the analytic result to the server. How's that? No servers, no CentOS, no speed problem, no bandwidth problem. So you see that was very convenient. If I could make this work, it would be a huge breakthrough. So I changed this and tried that for, but the only problem I had, I gotta just be honest, was synchronizations. And I totally got rid of the frame synchronization process, because when I was processing each frame here, I was saving that frame with the timeline, or date time, and then pushing that to the server, and then aggregating based on the time, each frames. So it was very easy. So I just removed whatever worked. I did on image synchronizations, which I filed for a patent as well. It was just wasted. So then, this is a slide that explains how that works. And let me skip. These are the various edge GPUs and the pioneers in the market. NVIDIA, of course, is the one I used. Google TPU. I got Google TPU in a conference again around the same time frame last year. It was a little kind of hard for me to make it work, but I made it work. But it was too late for me. I was using Jetson TX2. And Intel offers a few on-edge GPUs, and could use that one too. And the requirement for on-edge compute is a commodity machine. You don't need a server. Because your servers are replaced with Jetson Nano, $99 each. So you need a commodity machine to install a database engine on that to save your data. That's it. And then on edge computing chips, again, it's very cheap. And you still need those cameras. What you need is minimal network bandwidth, which we used to spend a lot of time on, and it costs us a lot to have a fiber line from camera to our servers. We don't need that anymore. With a little algorithm optimizations that I had using TensorRT, I changed the algorithm size to be compatible with Jetson Nano, and then synchronization issue was gone, and then it complies with regulations in terms of security as well. And which one is better, on edge or on premise? We don't know. It depends. If you have a low bandwidth and higher security in place, then on edge is better. If you have higher bandwidth, no problem with the bandwidth, and the low security, then I believe on server is better, on premise. So thank you very much. And we have a few minutes to take questions. Go ahead.
Can I take 2 questions, please?
Sure.
First of all, thank you so much for the fantastic session. I really like the fact that you opened it up with the generative analysis networks.
Sure.
So, but you didn't touch upon it. Would love to have your views on that, especially with regards to what the data. So if you can actually talk a little bit about the usage of GAN in
Uh-huh.
the project, that would be awesome. And the second question is, now in slide number 13, you had about 50 cameras streaming data real time all the time, right?
Mm-hmm.
And streaming cost is GPU is larger. The compute power is heavier, the same time the price of the pipeline is very huge. Did you ever try to make sure that you reduce the noise in terms of making sure that if I'm getting data, for example, from an electron microscope, I only need those images which have better pixels, better quality, better workflows. I only pass those through my streaming data
Mm-hmm.
and jump out of it.
Okay, I'll explain. Thank you very much for your question. Again, that was a very interesting question. I implemented this process, the whole pipeline, and it was working fine starting at 9 a.m. to 5 p.m. And then prior to that, as I mentioned, we had lighting issues. And the prediction was just so crazy. It was a crowd count project specifically, but it was just showing erratically. It was just showing how erratically model predicts. In like, for example, in 6 a.m. you don't have anyone in the facilities. It was just showing 100 people are there, and those were because of the noise of the images. Okay, so how I solved that problem? I used those noise and created again to have a clear version of my frames. Okay, and I couldn't do that when I was doing on-premise when I was going with on-premise architecture. I had to push data to that server to be able to process this stuff because I couldn't just use camera servers, which is called Synology server. They had their own proprietary software to install that, and it was close to camera. I couldn't do that. I had to just push data, the video stream to the server to be able to do that, and that was a huge problem. And the failure, as you mentioned, that's not a joke. 15 cameras, live 4K stream. It's a lot of data. But hey, we are Comcast. We own a lot of bandwidth, right? So we can handle it. Well, I just asked for fiber, and they gave me fiber. So that is, I use GAN and those filters to improve those images for the time frame between 6 to 9, and then 5 p.m. and after, to get the quality image. So if you want, I can share detailed information on what type of GAN I used for that. That was a pretty cool experience, though. Pardon? So I'll share with you what kind of architecture I used. And the second question was about?
In terms of making sure that
Yes. So as I said, I didn't have the luxury to have a computer, another machine close to each cameras to be able to do the image processing before just pushing that data to the pipeline, to the wire or fiber. So that was a huge challenge, which was resolved basically with on-edge compute. And later I changed the camera to the 8K, as I mentioned, and 8K Access offered some noise cancellations. They have their own software, and better image quality, really very brittle, very clear, and they could control lighting conditions as well. And then I removed that GAM model from the pipeline. So that's how it works. Any other questions? Okay. Yes, go ahead.
So if you compute on the edge, then I mean, depending on the application, then passing the images on to the server.
Ah, that's a great question. That's a great question. Oh, that was a big challenge. Yes, you have to process those images. So I removed, as I said, the image synchronization part from the pipeline when I moved to the on edge compute architecture. But I had another problem. That was a problem. So you have to deal with raw frames. So that's that's not in my expertise and skill sets, but I had a friend who's a very proficient in C++ programming and in a very low level dealing with raw images, like in the level that people who wrote OpenCV. You're not using OpenCV, you're using something before OpenCV. So he just gave me that piece of code. I could process the raw images. So even OpenCV cannot do it. Yep.
So similar to that, did you try or consider a mixed model where you do just the image processing and then try and reduce bandwidth on edge, but then do synchronization and neural net on server?
Synchronization was gone because I was not doing synchronization for on-premise.
That's what I mean. Did you consider doing both?
No.
Which would then require synchronization, but potentially less bandwidth if you do some filtering and frame dropping on edge.
All right. Well, the frame dropping or the quality of the image was totally disappeared when I used 8K cameras. So it was not an issue. So I did not consider that. Any other questions? Okay, the next speaker would be